Okay, this is from our textbook. It's chapter 12. It's section 12.3, maximum and minimum points and optimization. Well, the first part is maximum and minimum points. It starts with the investigation 4. The number of bacteria B in thousands in a culture at time t minutes is given by the formula. So they give us the formula. A, sketch the graph. So when it says sketch, just pick up your calculator, put that all into your calculator. Remember this restricted domain here. T is on the x-axis. And make sure that when you do sketch it, that you limit it up to t of 40 only. Okay, it looks like they've made a bit of an error here. They've used x, but they've got a t here. Okay, to be consistent, if they put a t here, they should be putting t's here, here, here. Okay, and also the domain is clearly t. So that should really be a t, and a t. Good, so we put it in the calculator and we have a look at it, and you see between in that range, in that domain, the range of that domain, so that domain, that limited domain there, restricted domain, you can see that it is kind of wavy. It peaks at one point there, and it drops and then goes back up again within 0 to 40. Now, to find the first derivative, it's just a matter of going back to the original function. They're the same, right? So we just use our differentiation rule, which is 3 times that number, and that 3 changes to a 2. It's 2 times that number, and that 2 changes to a 1. And it's 1 times that number, and that becomes x to the 0, which is 1. And the derivative of a constant is 0. So we're going to have, that's how we get the derivative function. Find the values of t when there are the most and the least bacteria. Okay, so the values of t where there's the most and the least is where, but in that domain, that restricted domain, we're looking for minimums and maximums. Remember, the number of bacteria is measured on the y-axis. Okay, within that restricted domain. So what happens is if you look at your calculator, you can see that there's a minimum and then there's a maximum. We've got to find the values of t. Well, the way to do it is you can do it, since it's already in the calculator, you should just use the analyze graph function and just go to minimum maximum, and then you can find what those points are. Now, if you wanted to use the derivative function, you just equate it to 0 and you solve for x. Now, because the original function was x cubed, a cubic, the derivative functions are quadratic, and so there's 2 solutions, and they're the 2 solutions where what we call stationary points or minimum and maximums. So we've found the 2. And then it says find the gradient of the function at the 2 points found in part B. That should say part C. So here, well, the gradient would be 0 because we equated the derivative function as 0. So that's basically saying that the gradient was 0. The slope was 0. Calculate the gradient of the function at a point just before and just after the values of t found in part B. Remember, when the derivative function is negative, it's a negative slope because the derivative function shows us a slope. And when it's positive, it's a positive slope. So if we go just before and just after the maximum and minimum points, we should see a change of slope. Okay. So if it's a minimum, then the slope is going to be negative, and then after it passes through the minimum point, it then becomes positive. And if it's a maximum, it's a positive slope, and then as it passes through the maximum point, it then goes to a negative slope. So knowing the sign, whether it's a positive or negative sign of the derivative, we can find out what the slope actually is. Okay, so that's a good exercise to do, and we've got an example coming up. Use your results to explain the difference between the local maximum and the local minimum. Okay, so we said that. We said if it's a local maximum, then it's a positive slope changes to a negative slope, so we recognize it as a maximum. And if it's a local minimum, it's a negative slope changes to a positive slope. Conceptual, how do stationary points help solve real-life problems? Well, we've got that coming up later in the video, and also in the next section on optimization. You can also use technology and solve for the derivative at derivative equals 0, as we pointed out, to find the value of stationary points. For a function, if the derivative equals 0, then the point is called a stationary point as the instantaneous rate of change is 0 at that point. So that's all that is saying is where the gradient is 0, we have stationary points. If the signs of the gradients are different on both sides of the stationary point, then it means it is either a maximum or minimum point. Now, this is important later on, and right now it's also important because it really identifies whether it's a maximum or a minimum. In many cases, we are interested in when a function reaches its maximum or its minimum, as in real-life cases, these points can be important. For example, if it is a function of profit versus a number of products produced, we would like to know where the profit is at a maximum. A stationary point can be a local maximum point or a local minimum point. at a local maximum or minimum point, the derivative equals 0, which means the gradient at that point is 0. If the sign of the derivative goes from negative to positive, there is a minimum point. Okay, they've started on this one. It goes negative. That's a negative slope, right? So it's coming in like that. You can imagine a curve like that. It's a negative slope, and then it's a zero slope or zero gradient, and then as it goes up the other way, it's going to be a positive slope. If the sign of the derivative goes from positive to negative, there is a maximum point. So you can imagine an upside-down parabola here, for example. It's going to be positive, positive slope, and it gets to zero slope, and then the other side is going to be a negative slope, and that's what that's saying. Hint, the local maximum or local minimum points may not be the maximum or minimum values of the graph. That's right, that's why we got this word local. You've seen this word local sneak in here? That's because we're given a restricted domain. Within the domain, the x values that we're looking at, they're called local maximums and local minimums because there could be others. Example 7, consider the curve S equals this. Find the derivative. Well, we've done that many times before. There's the answer there. It says using the usual rules for differentiation, but with the new notation. Okay, the new notation, they'd like you to use ds dt rather than what we saw previously where we've got the dash. So that's an easy one to do. We can all do that. 3 times 3 is 9, 9t, and 3 minus 1 is 2, so it's 9t squared. 2 times 2 is 4, times t to the power of 2 minus 1, which is 1, so that becomes 4t. And the last one there is just, assume there is actually a 1 there, so 1 comes down, that's minus 4. And then the t becomes 1 minus 1, which is t to the 0, which is equal to 1, so that becomes minus 4, and the derivative of a constant is 2. B, on the same axis, sketch this and its derivative. Okay, we can do that. What I'd like you to do in your calculator is to do what we've done here, and we've done this in class before too. Make sure you always identify which is the original function. That's the original function there, and this one here is the derivative. They want you to plot both in the calculator, and it says sketch, so put them both in the calculator and just draw them. Okay, they haven't given us any restrictions on the domain or on the range, so it doesn't say. So just use your imagination how you'd want to do that. Just get all that on the screen and then sketch it. Find these points. You can find that point by using analyze graph and putting the dotted lines on either side, and you'll find the maximum there, the local maximum, and the local minimum of that. And then that's the actual original one. Now, how do we know that's the original one? Because that's a cubic. Okay. How do we know this is the derivative function here, the purple one? Because looks like a parabola, and we know a parabola's got the squared term in it. Okay, now we saw this in class. What does this purple one actually represent? It represents a slope. Anything above that line, the x-axis, means it's a positive slope. So that's positive slope, positive slope, positive slope to here. Okay, and now we're going negative slope, and that's why the derivative function is all negative here. So it's all negative, and it gets to here, and then it goes positive again. This point here, it's positive now. This purple function is positive. It's above the x-axis. It's positive. Okay, so that means the slope is positive because the y-axis is representing the slope, the sign of the slope, whether it's positive or negative for the derivative function. And then when it gets to this point right here, you can see that the slope of the original function, which is green, has become positive again. So that's what that's representing. And you can either plot the curve found in part A or use the derivative function on the GDC to do so. Use your GDC to find the roots of that. Okay, so you can basically, to find those 2 points, you can just use polynomial tools, put that in, and you can find out what those points actually are. Okay, we're still with example 7, and it says solve the equation ds dt equals 0. So we're finding out at what points, what values of t will make the derivative function, which we've got up here. This is from the previous page. What values of t will make this equal to 0 here? So 0 equals all of that. And we got these 2 answers. It says this observation provides an alternative method for solving part C using the GDC to find the maximum minimum points on the original curve, as we looked at on the just previously now with B. We can find those points by using the calculator, the analyzed graph maximum and minimum points. You can use that function of the calculator. Or you can just solve for t here, and you can do that by equating the derivative to 0. Okay, that's our derivative function, and solving for t. And then obviously there's 2 answers because it's a quadratic. D, state the feature of S equals 3t cubed plus 2t squared minus 4t plus 2 indicated by these points. Okay, so what we can say the feature is that When the derivative is set to 0 and you find t, those values of t, which are in the purple one, right? The purple's representing the derivative function, that will be equivalent to a stationary point on the original function. Now I'm calling it a stationary point. It's a local maximum. We can see that from the graph. And this other one here, when it equals 0, remember that's a derivative function. So when it's 0, it's 0 equal to 0 on this axis. It's equal to 0. And when you go up there, that's a local minimum, or we'll call it a stationary point. That's what that feature is. It says each of these values of t give a stationary point. One is a local maximum and the other is a local minimum. The maximum minimum values, sometimes called the global maximum minimums, are at the end points of the curve. Okay, now what that means is they're calling it global, not local, because you can see we're calling this a minimum, but it's not really the minimum. The minimum is all the way down here. It's going down all the way down. And that's not really a maximum. It's just a local maximum because we can see that the curve does go forever. If the domain of the function is restricted, now we're restricting the domain. We're saying that t has got to be greater than or equal to minus 2, okay, which looks like about here, there. And t is less than or equal to 2, there, so we've restricted the domain. Find the actual maximum minimum values of the function. Now it's the actual maximum minimum because we've stopped, the function stops at minus 2, t is minus 2, and t is plus 2. And it says what is the actual ones. Okay, and as you can see from the graph, if you stop that at 2, it's going to be down here. It looks like minus 6, so somewhere off the graph. And the other one, if you stop it at 2, well, it's going to go up, 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 up. And the actual maximum is going to be up here, which looks like about 26 off that graph there. Okay. Let's have a look at example 8. Consider this curve, y equals x plus 1 on x, with this restriction here that x cannot equal 0. A, find an expression for dy dx. Well, remember, to get this answer here for dy dx, the first thing we need to do is to rewrite this. Make sure that you're not using fractions in your algebra. So the way this would be rewritten would be x plus x to the minus 1. Okay, x plus x to the minus 1. So we find an expression for that, and that would be, if that was x, that's going to be 1, the derivative of that, and minus 1 on x squared. So if you consider that as x plus x to the minus 1 and use the rules of differentiation, you'll end up with that answer. And then it says sketch the curve. Well, just put that in the calculator. Okay, it says sketch the curve. Now, when it says the curve, it doesn't say the derivative. And so what we're looking for is this one, the original function. That's the original function. Now, you can see here it says x doesn't equal to 0. So that's an asymptote there. And you can see there that this gets closer and closer to the y-axis, but it doesn't reach it. And on this side, it does the same because we can't have a value for x equals 0. Sketch the curve, so we've done that. Use the calculator and just draw it. There's no restrictions on the domain except for that x, so you'll have to clearly indicate that's an asymptote. B, sketch the curve, right? C, find the coordinates of any local maximum or minimum points. Okay, so it looks like we've got on your calculator, you'll see this. That looks like a local maximum. That looks like a local minimum. You can use analyze graph and you can find out what those points are. And they're calculated and they're right here. These points can be either found by solving equals 0 or by using the GDC. We recommend use the GDC. If you want to use dy dx equals 0, you put 0 equals 1 minus 1 on x squared and you solve that for x. Okay, D, find the gradient of 2 points, close to but on either side of the minimum point. So we want just to the left of that point and just to the right. They've chosen 0.5 because we know that point is at 1, right? X is 1. So just to the left, just to the right. And then they put it into the derivative function, which is here. And they get minus 3 for 0.5. We expect that. It has to be a negative slope, so it's negative. And then when we just to the other side of it, 1.5 we chose, then it was positive. The number is positive. That's all you're really interested in, and it's a positive slope. Any points will do as long as there are no discontinuities or other turning points between them and the local maximum or minimum. So we just chose to the right and the left. As long as it's not doing something weird on either side of that point, you can take any point. And as long as there's no major changes in the slope of it, there, that's just going nice and smooth. And so we've got that for D, and we've noticed that it's negative on the left-hand side, the slope is, and it's positive on the right-hand side because that's what we're getting from this formula, and that formula, the derivative function, gives us the slope, or the gradient. Explain why this shows that the point found is the local minimum. Well, the gradient changes from negative to positive. Here it's negative, and it shows us as negative. We've got a negative number. And then once it goes past this stationary point, it's then positive, so that indicates a minimum point. Okay, exercise 12E, questions 1, 2, and 3, and 4, 5, and 6.